Hello students, welcome to this lecture series on approximate methods in quantum chemistry. I am Sabyashachi Mishra from Department of Chemistry, IIT Kharagpur. In next several hours, we are going to discuss different approximate methods and how we can apply them in quantum chemistry. Before we discuss anything any further, let us try to understand what this course would entitle. Let us start by from the definition of this, the terms that we are using for the name of this course. We have this so-called quantum chemistry. What is it? As you know that quantum chemistry is essentially application of quantum mechanics in chemistry related problem or in the chemical world. What do I mean by when I say chemistry related problem or chemical world? You see, whenever the chemistry deals with atoms, molecules, large molecules, even including biomolecules, solid state systems, wherever there are atoms, interaction between atoms, formation of molecules, sharing of electron, bond formation, bond breaking, all these places chemistry is very important. And if you notice, we are discussing about the formation of bond, the breaking of bond, the sharing of electron. You all know that these are purely quantum mechanical phenomena. So therefore, to explain this, to understand these processes, we must use the principles of quantum mechanics. So whenever we use principles of quantum mechanics and apply to chemical systems, that also includes biochemical systems, extended materials, we call that field as quantum chemistry. Now, what are these approximate methods in quantum chemistry? You would realize by now from your earlier experience with quantum chemistry that when we say that we want to solve a system quantum mechanically, we often have the following in mind, that we want to solve the Schrödinger equation corresponding to the system. Now, the Schrödinger equation, very simply H psi equals E psi, is very easy to write down this equation, but it's very difficult to solve it. So much so that we could only solve a handful of problems exactly. What do I mean by that? See, by exact solution, I mean that when I can whether I can solve the Schrödinger equation, obtain the eigenvalues and the eigenfunctions in their closed analytical format, or in other words, their exact solution. There only exist a few very simple model systems that can be exactly solved. The largest or the most complicated system that we can exactly solve quantum mechanically happens to be hydrogen atom. But as you know, as students of chemistry, hydrogen atom is perhaps the simplest of all chemical systems, because whenever we go for larger atoms, of course they are more complicated than hydrogen atom. Whenever we talk about a molecule, even a small diatomic molecule, that is also more complex than hydrogen atom. So therefore, what quantum mechanics can solve exactly kind of is the starting point in chemistry. So therefore, we have come to this situation where we see that quantum mechanics is invaluable, it's essential to describe chemical features, chemical processes, but also the solution of a chemical problem quantum mechanically is extremely difficult. So when we cannot solve them exactly, what do we do? When we cannot solve a problem exactly, we see if we can find an approximate solution to it. This is exactly what we are trying to do in this course, that we are going to see what are these approximate methods using which we can solve chemical problems. Now, the approximate methods that we are going to discuss in this course, we are going to use it for smaller systems so that we can solve them reasonably well, but these very methods are robust enough to be used for even larger systems, because we are not going to always solve the problems analytically, but we would also solve these systems numerically. When we solve a system numerically, it becomes straightforward, or the path becomes clear to extend this method to larger and larger system, because in that case we simply require more computational power. With increasing access to large computers, we are now able to solve quantum chemical problems in large system. For example, we are now studying enzyme catalysis. We are studying about reactions happening at extended surfaces. And also we are studying various type of organic and inorganic reactions, their reaction mechanism, thermodynamics, kinetics using quantum chemistry. So the materials that we are going to discuss in this course are going to be fundamental in that sense, and they are all used in today's in real life, modern research in quantum chemistry. So let us get started with the discussion of our course. But before we look at the approximate methods, let us try to review those simple systems where where we can solve the quantum mechanical problem exactly. In fact, before that, we also want to discuss about why was there even a need for quantum mechanics. So briefly, we will go through the stories of origin of quantum mechanics. There are a few experiments at the end of 19th century and beginning of 20th century that puzzled the physicists of that time, because the existing knowledge in classical physics was not sufficient to explain those experimental results. One such experiment is the so-called black body radiation. So when we look at a substance, when we look at a body and identify it with by its color, what do we understand from there? We understand that if a body has a particular color, it means that when light falls on this particular body, the body absorbs all colors except for the color that it manifests. That color gets reflected. So that's the story of a normal body that we see. Black body is an ideal system which absorbs and emits all radiations, all colors. Now, when you hit black body and then you observe their emission spectrum or their the spectral density, that means which wavelength do they emit by what amount, this is what we get. For example, this plot that you see, it shows the spectral density versus wavelength. The different curves that you see in this diagram represent the black body radiation at different temperature. For example, the red curve that has maximum area under it corresponds to the black body radiation at a very high temperature. As you lower the temperature, you see the green curve, the orange and the blue curve. The thing that you should notice is that as at lower temperature, the area under this curve is steadily decreasing. Now, this spectral density, this is what we observe from experiment. Now, why is this so important? Because we can use this concept to see what kind of bodies should we use for energy harvesting. At what temperature should we hit the body and then look at its spectral density, because this also amounts to how much of energy that this system is trying to release. So to understand this, Max Planck took up this problem and thought that he would like to explain as to how or what is happening at different temperature with this black body radiation. The existing knowledge at that time from classical physics showed what is the expected behavior. That expected behavior is shown in this dashed line. As you can see, so this dashed line is obtained from Rayleigh-Jean's law, which said that the spectral density should be inversely proportional to the fourth power of the wavelength. So now you see, when you plot Rayleigh-Jean's curve at different wavelength, it simply goes up and up. It never comes down. So that created a strange situation which goes by the name ultraviolet catastrophe, because you see at higher wavelength the Rayleigh-Jean's law matches with experimental outcomes, but as you go for lower wavelength, that means higher energy, you will see that the discrepancy is huge, and this leads to the strange situation saying that the black body at any temperature can emit infinite amount of energy. So that is of course absurd. So what is happening over here? So this problem was solved by Max Planck. The key idea that Max Planck invoked here was that the black body is made up of some material. So consider them as some oscillators that absorb and emit radiation. Classical physics said that these oscillators can absorb and emit radiation in a continuous manner. So that means it can take any energy along the spectrum. But what Max Planck invoked is that no, the energy of these oscillators of black body are quantized. So they cannot take any energy, rather they take certain value of energy. They absorb as well as emit a fixed amount of energy that gets decided, of course, by the prevailing temperature of the system. Now what he invoked is that energy of these oscillators are proportional to the frequency of the radiation. So by using this, instead of calling this energy of the oscillator as a continuous function, he said that the energy of the oscillators are quantized and the absorption and emission occurs only at certain quantized values. So therefore, instead of using this wavelength or frequency as a continuous function, he used it as a discrete set of functions. So in that case, the algebra changes, and he could, using that concept, he could reproduce the experimental result, and to obtain this experimental result, he finally had to use this proportionality constant as h, and this h we know as Planck's constant. So here what he assumed is that the energy of these black body oscillators are quantized. So this is a very new concept that was put forwarded by Max Planck to explain this black body radiation. Around the same time, there was another experiment that was puzzling scientists, that was photoelectric effect. The photoelectric effect is the simple process where you shine radiation upon a metal surface, and then by that metal loses electron, and this lost electron, the photoelectron, if you connect it to an electric circuit, you can monitor this electron in terms of current. Now this experiment these experiments were being carried out and the results were obtained, but then there were some anomalies in these experiments. For example, when you plot the frequency of incident radiation against in the x-axis and the kinetic energy of this emitted photoelectron in the y-axis, the experiment showed that there is some linear dependence of the kinetic energy of the photoelectron with the frequency of incident radiation. Not only that, it also showed that certain radiation whose frequency is having certain values, they were not able to emit any photoelectron no matter how strong, how intense radiation, how intense light you were using for that. Some frequencies were simply unable to eject photoelectrons even if you use very high intensity light. But in some other cases, some other frequencies, even when you are using very low intensity light, but those radiations could easily eject photoelectrons. So this was puzzling at that time, because at that point of time it was thought that the energy of the light lies in its intensity. So therefore it was expected, no matter which color light you use, as long as you are using an intense, very highly intense light source, the intensity is large, you should see photoelectrons quickly, and also you should see the increase in kinetic energy of the photoelectrons. But the experiments were not showing that result. So this is where Einstein comes into picture, and Einstein proposes that okay, we can explain these things, but for that we have to make some assumptions again, that the energy of this light, the radiation, is proportional to frequency, very similar to what Max Planck proposed in his black body radiation. And by again looking at the experimental result, it turned out that this proportionality constant happens to be the same h, or Planck's constant, as we saw in the black body radiation. So therefore, in Einstein's work, he also said that the energy of this incident radiation is given by h nu, and it is proportional to the frequency. Now, where does the intensity come into picture? The intensity comes into this picture in the following way. Einstein proposed that when light falls on the matter, it's not a continuous process, rather a light of a particular color contains a fixed amount of energy, and he called them photon. This photon's energy is determined by the frequency of this light. Simply multiply by this constant, Planck's constant, and you get the energy of that photon. Now, when you use high intensity light, you simply give more and more number of these photons, or more and more number of these energy packets. So when you have more and more number of energy packets, so each packet can eject one photoelectron. So therefore, Einstein proposed that this light, which we normally believe as a wave, is actually a kind of acting like a particle, as if one particle, that is light, coming and hitting another particle, that is electron, and it hits the metal surface, and another particle, that is electron, gets ejected. So as if it is interaction between two particles. So Einstein proposed the second thing, that light, which is typically known as a wave, has particle like nature, and the energy of the light is called photons. So they come in fixed packet of energy depending on their frequency. So if the frequency is low, that means the energy of each packet is very low. This energy is not sufficient to eject even one electron. So therefore, even if you put 10,000 number of packets, since each packet is not able to eject an electron, 10,000 packets are not going to eject even a single electron. That is why we see that even when we use large intensity for some frequency, lower frequency light, we are not able to see any ejected photoelectron. So the two concepts that Einstein proposed is that light is a light has particle like nature, and the other concept is that the photon, the energy of the light, or the is called photon, and this metal absorbs the light energy in terms of these photons. So once we understood these two concepts, particle nature of light and the energy comes in fixed quantized values, photoelectric effect experiments were easily explained. So now we see two unrelated experiments coming and hitting upon one constant h, which turns out to be an universal constant. Okay, now we go to another experiment which puzzled the scientists at that time, and this relates to the emission spectra of atom. The picture that you see here is a cartoon representation of a typical emission spectra of an atom, where you see several discrete lines followed by a bunch of closely spaced lines looking like a continuum, then again some separation, and then some discrete lines followed by a continuous lines, and so on and so forth. For hydrogen atom, when the emission spectra were recorded, it was very puzzling, but as you know the story, there were Lyman, Balmer, Paschen and so on. They could fit one group of lines by using some equations, and finally Rydberg came forward and gave another fitting to another equation that could reproduce all these bands together in case of hydrogen atoms emission spectrum. So using Rydberg's formula, we could actually obtain one-to-one correspondence of with this emission line, but that did not give us any physical insight. What was required was to understand what might be happening in the system when we record emission spectra, so that we get this kind of features. So this was given by Bohr in his Bohr's atomic model. In Bohr's atomic model, Bohr assumed again something to be quantized, and it so turns out that Bohr made this as assumption that the angular momentum of electron are quantized. Where does this angular momentum comes in? So, in typical Bohr's atomic model, you see that there is a central nucleus, the electrons go around the nucleus. So, Bohr suggested that the electrons go around the nucleus in fixed stationary orbits, and while they move around, their angular momentum is quantized. They have fixed values of angular momentum. Angular momentum is not continuous value, rather some discrete value of angular momentum are allowed. Once Bohr made that assumption, of course there was some balancing of forces operating in the atom. There are small exercises, I am sure you have done this maths earlier. So, once Bohr figured that part out, then Bohr ended up with some energy labels. So, these are typical energy labels that Bohr's number n equals 1, n equals 2, n equals 3, 4, so on. And then you see after some discrete line, when you go sufficiently above, you see the energy spacing between two neighboring lines is very small. So, we are representing them as a continuous line. Now, in case of emission spectra, how does it happen? Bohr said that the emission spectrum is obtained when the electron jumps from one higher energy stationary orbit to lower energy stationary orbit. So, we see depending on by drawing this way, we can reproduce different either Lyman series, Balmer series, Boston series, and so on and so forth. So, Bohr's atomic model could give a physical interpretation of Rydberg's formula. Of course, Bohr's atomic model had its own shortcomings, but the success of Bohr's atomic model in case of at least explaining the emission spectrum of hydrogen atom was primarily due to this interesting assumption that the angular momentum of electron is quantized. And of course, that also led to the situation that there are the radius of the stationary orbits are also have fixed values. They are not any arbitrary value, so they have fixed values. So, now again and again we are experiencing that things are quantized. That was quite puzzling, because we see that n equals 1, 2, 3, 4, so far like as if these numbers, natural numbers, are very important to Mother Nature. We always thought, human beings always thought that this the numbers 1, 2, 3 are something that we invented to count our sheep. We thought that they are no different from any other real number, 1.1, 1.2. This is what we had always thought, that the natural numbers are our invention. But now here we see again and again the system in the nature in its various forms, various manifestation uses them. The oscillators of black body radiation, the energies were quantized. Energy of electromagnetic radiation, quantized. Angular momentum is quantized. So, now this quantization of many different observables are coming into picture. So, these are three groundbreaking experiments that clearly expose the limitation of classical physics as it existed back then. Now, we will discuss, apart from these three experiments, there are two great ideas, theoretical ideas, which are not really found inspired by or compelled by experiment, but there were ideas of their own which were groundbreaking and phenomenal. So, these two ideas, for the first of them is the so called de Broglie's hypothesis. Remember, when we are discussing about photoelectron effect, we said that Einstein suggested that light, which is regularly is typically believed as a wave, has particle like nature. Now, de Broglie in his hypothesis suggested that like light, any other particle that we see, the particles that we see of course are particles, but they also have wave like nature. that was very puzzling. That was against our intuition, because what de Broglie was suggesting, that these electrons, the nucleus, or even you extend it to classical world, everything that we see as a particle which has a mass, which is moving at its velocity v, therefore has got a momentum p in this equation, has a wave-like nature. Now, if it has a wave-like nature, how would you explain that wave? How would you characterize that wave? De Broglie's answer to that question is that if a particle with mass m moving with speed v, or in other words has momentum p, it is associated with a wavelength. Now we call it as a de Broglie wavelength, which is given by lambda equals h by p, where h is again the Planck's constant. Now this was a great idea. De Broglie's hypothesis actually helped prove Bohr's atomic model even in a more systematic way. But now the wave particle duality gets a complete shape. Einstein's proposition was light, which has both wave-like and particle-like nature. Now de Broglie's hypothesis is that any particle that we see has also a wave-like nature. Now wave particle duality is complete. Of course, when you look at the classical world, when the mass is very large, speed is so therefore the momentum is very large. So you can see from this equation the lambda or the wavelength is very small. So in that case the de Broglie wavelength is very small. So that otherwise we can also extend it to the classical world, except for the fact that in classical world de Broglie wavelength is so small that it doesn't make sense to be called as a wave. Now the second groundbreaking idea was the Heisenberg's uncertainty principle, where Heisenberg suggested that, well, there is this great concept that you cannot simultaneously and precisely measure two quantities, for example position and momentum. In the future classes we will discuss about the mathematical argument behind them, but Heisenberg's uncertainty principle said that if you want to determine the position of a particle precisely, you have to give away your right to know the momentum of the particle exactly. So simultaneous and precise determination of position and momentum is forbidden. It is not an experimental limitation that one day someone would construct a better equipment with which you can determine the position and momentum of the particle simultaneously and precisely. It is inherent nature of the system, quantum mechanical system, that position and momentum cannot be simultaneously and precisely determined. They would have to follow a minimum uncertainty. This minimum uncertainty is given by this h by 4 pi. So the uncertainty has to be always greater than this value. Now you can classically imagine, because when you try to locate a particular particle in space, you would probe it with a certain wave, a light with certain wavelength, and that light, with the wavelength of that light with which you are probing the position of the particle, must be very small so that you can locate the particle precisely. But when you make the wavelength of that particle very small, the momentum of that light, which also has a particle-like nature, according to de Broglie's hypothesis, the momentum will be very large because the wavelength is very small. Now this particle which has a large momentum, when it goes and interacts with the particle whose position you are trying to determine, there would be a transfer of momentum. Now the transfer of momentum will simply change the momentum of the particle that you are initially trying to find the position of. So therefore, if you want to precisely determine the position, there will be an uncertainty in momentum, because the very act of measurement of the position will compromise the momentum of the particle. So therefore, you have to give away your rights to learn about the momentum of the particle precisely if you want to know the position of the particle precisely. So basically these three experiments, the black body radiation, photoelectric effect, the emission spectra of atoms, plus these two groundbreaking ideas, the de Broglie's hypothesis and Heisenberg's uncertainty principle, exposed the limitations of classical physics, and then there was a need of a new mechanics, and that's how quantum mechanics originated. And with the growth of quantum mechanics, how we have come forward, that is the part of the story that we would continue in our next lecture. Thank you for your attention.